All right, here we will go over some different acquisition modes of SAR. We have gone through the theory part of SAR, but mostly for street map data. Now we'll see some variants of it, like ScanSAR, TOPS, and a little bit about SweepSAR as well. So ScanSAR basically is a time division multiplexing system. You could divide the orbits into different parts to observe the different areas on the Earth's surface. For example, you can illuminate a certain part of the ground for a given period of time, and then move to the next subspace, what we call it, and then keep doing the same thing, and then come back to the first subspace. You do this periodically, and after you process the data, you get a ScanSAR image. So each time the satellite observes a certain area on the Earth, we call this a radar burst. The purpose of ScanSAR could be largely illustrated by this figure here. The smaller box in the footprint is actually a frame of ALOS-1 street map data. The larger box is the footprint of ALOS-1 ScanSAR data. If you want to map the Earth at a very, very large scale, for example, here, the San Andreas Fault, actually ScanSAR is the way to go because it's just simply much more efficient than doing street map mode acquisitions. ScanSAR has its advantage of covering a large area on the Earth's surface, but it also comes with a cost. First, of course, is the resolution along this azimuthal direction will get degraded, and it also requires the illumination to happen at the same location every time your observation is made on the Earth's surface. All the radar bursts must like overlap, so as you can do interferometry. The plot on the right sort of shows this theory that the radar bursts had to be matching with each other every time this acquisition is made. The reason for that is basically you have to illuminate the ground from the same part of the orbit. If they are misplaced, for example, if your reference is mirroring this location from this segment of the satellite orbit, where your repeat acquisition is being made over a different part of the orbit. Basically, you are looking at the same target, but from different or slightly different angles. In that case, your return signal wouldn't be coherent with each other. If things work well, you get all the bursts aligned. You get coherent fringes, like this one shown for the 2014 Napa earthquake. This is the post-seismic pair that shows some deformation after the earthquake. This is ALOS-2 ScanSAR data, by the way. If you are unlucky and you get nothing overlapping, you get no overlapping radar burst, basically you get nothing in the interferogram but noise. An earlier analysis from Xiaopeng showed that with the drift of the burst overlap, the coherence generally drops, and you need roughly about like 20% of burst overlap in order to get your interferogram into a coherence of about 0.2, which is roughly a level to get usable fringes from your interferogram. And ALOS-1 had this burst drifting problem, so its ScanSAR data are largely unusable for like interferometric purpose. The right-hand side sort of shows an example by Xiaopeng that the fringes are coherent when the bursts are overlapping, but when the bursts start to drift, you see a drop of coherence, and you start to lose signal. Here's another example by Morishita, that is from the early ALOS-2 ScanSAR data over the Hokkaido island of Japan. This has about like 19% of burst overlap, and you need to do a lot of filtering to get coherent fringes. Actually, if you dig into this pair just a little bit further, you can almost directly see how the radar bursts are misaligned. The two images are placed next to each other by aligning the coastlines from these islands, and you can sort of see the center of these bursts are actually misplaced. They are off by about 340 lines, and the width of this burst is about like, I think, 420-ish, So that's about like 20% of burst overlap left in this image. And you can almost predict what's going to happen when these bursts are not overlapping with each other. Later on, Ryo Natsuyaki from JAXA found that this burst drift has about like 56-day cycle for the early data, and they fixed this, I think, in February 2015 by reducing a line in a certain burst, I think, if I remember correctly, to prevent the burst from drifting. And yeah, like I said, that's fixed in February 2015. And right after that, that's the 2015 Nepal earthquake in March. And it was just in time to capture this large event. I think this is the first time that ALOS-2 ScanSAR data captures such large events. And you have a comparison. If the data is in strip map mode, you see that only part of the rupture is captured. Thus, ScanSAR is really ScanSAR really has its advantage in terms of capturing these large events. However, we also noticed that sometimes you get these strange misalignment, even though all the other seems to be coherent and things are running fine. So what really happened to this ScanSAR image? Turns out because for ScanSAR, you are essentially making observations through different part of the orbit. So you get this issue called interference between these slits. That's sort of described by this experiment on the top left. What's shown here is actually an example. The top right plot here is actually a focused image of the two corner reflectors at pin and flat, but from strip map data. So after focusing, these corner reflectors will be just two very bright spots in the image. But if you look at the ScanSAR image, this is upside down, by the way, you see that every one of these scatters are being interfered and they show up as like a series of scatters. The problem from last slide is actually when you're doing cross-relation, or in other words, trying to match these two radar images together, these peaks might be misaligned to its secondary peaks. So that's why that part of the image is misaligned and have this decorrelation issue. However, luckily, these side dots or side lobes are not too close to the center, so we can start to do some tuning to make sure that the correlation happens only on the major peak to avoid such situations. Other than the interference problem, ScanSAR also has this problem called amplitude scalloping, which is due to the burst acquisition mode of this radar. The fringe here, the figure here shows the difference between a strip map mode data and the ScanSAR data over the same area. You probably noticed that the amplitude is not really stable for ScanSAR. So at the places where the satellite is illuminating the ground directly, you have a bright stripe. But at the places like in between these illumination, you have a darker stripe. This might be buggy for certain uses. So that's why like the SAR engineers have developed this new mode called, or new type of ScanSAR called terrain observations with progressive scans, or TOPSAR acquisition mode. The idea is really simple, that when the radar is scanning a certain subswath, the antenna will sweep from backward looking to forward looking. Thus, the amplitude will be maintained around the same level. It still has some scalloping, but much smaller. Then you scan the next subswath and then come back to the first subswath. The idea sounds really great, but of course, when these new techniques comes around, it also comes with new challenges. And the major challenge is that it introduces an extra Doppler along the track direction that is beyond the Nyquist, or in other words, the pulse repetition frequency here. Remember that it was discussed earlier that the PRF has to be large enough or larger than the Doppler in order to capture the full spectrum of it, so that you can do all kinds of like resampling of the data, all those kind of manipulations. But if your Doppler goes beyond the Nyquist or beyond your sampling, then it is problematic. So because of the existence of this sweeping antenna, this extra Doppler actually is much larger than the traditional Doppler you have just from the MO or the satellite. Turns out if you unwrap that spectrogram, you will get the difference between the forward-looking and backward-looking spectra being about 4.5 kilohertz. And currently, I think no PRF is as high as that. One issue, of course, is that since the spectral ramp is higher than the PRF, one could not directly sample the image as that will cause aliasing. This also means that any azimuthal misregistration will be magnified by this spectral difference and get reflected in the interferogram as burst discontinuities in the radar phase. A rough estimate is one has to co-register image to better than 1,000th of pixel to be able to see any not see any discontinuities in the interferogram. So how are we going to do this kind of precise correlation? It's sort of the key of processing the TOPS data. Traditionally, what is used for correlation is called cross-correlation. Basically, you cross-correlate different part of the image, calculate the transform function based on the estimated offset from cross-correlation, and then resample the radar image based on the calculated function. But the accuracy of these kind of estimates is roughly around 0.1 pixel, which is far from enough to do correlation for TOPS data. So we turn to another approach, which is to co-register the radar image purely using the information from satellite orbit. This heavily relies on the accurate orbit product from Sentinel-1, or whose accuracy is around like 2 to 3 centimeters in range direction and about 5 centimeters on the azimuth direction. Basically, you calculate the position of a given point on the ground in the radar coordinates for the reference orbit and also for the repeat orbit. Then there will be differences between them. And that difference is actually the offset between the two radar images. Then using those information, you can basically calculate how much shift you need to resample one of the image to match the other. Here is a brief comparison of the two algorithms. The deramping and re-ramping is to remove the spectral ramp so that you can resample the data or resample the radar image properly. The correlation is done using the estimated offset from the orbit file. Another difference between these two is that because geometric calculation is kind of fast compared to cross correlation, you can essentially do this kind of offset estimate pixel by pixel. Actually, this pure geometric approach works better in cases where you have an elevation change in your map. After geometric correlation, the phase map is pretty much continuous. The correlation image still has some seams at these burst boundaries. They are a little bit hard to see, but that's mainly because across that line, the radar has forward-looking and backward-looking beams that are not coherent with each other. Sometimes it's because burst offset, but that's kind of rare. The generic modules works really well. Here's a test that we did like years ago, that if you sum up all the acquisitions or interferograms from one way or another, you sort of end up with same radar phase. And if you close the loop, or in other words, you sum from one way and subtract from another way, you end up almost with 0, which is shown by the bottom right plot here. Lastly, we do have this module in Gmtsar called Enhanced Spectral Diversity, which basically is a way to improve image correlation by estimating the radar phase across this burst boundaries. And by plugging that phase difference into this formula, you can improve your correlation if you know the spectral difference and your PRF. So after enhanced spectral diversity, you see that most of these discontinuities will disappear and the correlation is better. However, this is not the default mode in Gmtsar for the moment, as we want the users to be a little bit careful when they're removing such kind of discontinuities. Some of these discontinuities are real, like orbit errors or misrestoration, but you have to notice that this azimuthal motion may not be just from the orbital errors. It could be from real tectonic motion. If your targeted area is something like for an earthquake or strong subsidence that happens in a short period of time, it's probably okay. But once you start to look like at small signals at tectonic scale, the problem will likely show up. Here's a summary of the processing chain of TOPS mode data in Gmtsar. I'm going to skip this as it's a little bit boring. All right, finally, Sweepsar. I want to cover just a little bit about how it works as NISAR is approaching, and it'll be in this new acquisition mode. Katya could probably add more to this part. So traditionally, traditional acquisition mode will transmit radar signals from their antenna directly. So the shape of the antenna sort of determine the footprint on the ground. That's why almost all the SAR satellites had the swaths or subswaths width being around like 70 kilometers. There, however, is another way of expanding the acquisition area, which is to use a reflector on top of your satellite and face your antenna toward the reflector. And this way, different parts of the antenna, when they are hitting the reflector, essentially they're going to arrive at different parts on the ground. You could do it similarly as Gmtsar, which light up the ground like one by one and record the returned radar echoes to form Gmtsar images. However, this is a waste of the potential of this design, as you are basically only using part of this antenna. Another idea is to just illuminate the whole antenna at the same time. You tune the face of them so the beam is focused at a narrow band on the reflector, and thus its footprint can be illuminating the whole swath. Then when the return radar signal hit the reflector, they will arrive on the antenna at different part and also at different time. So basically the ground is being swept at the antenna, which is also called sweep on receive. If you tune this properly, the antenna essentially can be used to receive multiple radar echoes, taking advantage that the radar echoes from different part of the swath arrive at the antenna at different time. And since this is sweeping, you could have multiple sweeps going on at the same time, as long as they are separated enough. And this way, you could also mitigate the effect of the low PRF caused by these wide swaths. Like traditionally, you had to give the radar echo time to sweep through this wide swaths, so the PRF could not be very high. But since you could allow multiple of them being received at the same time by the antenna, you can basically go beyond the limited PRF. So what's shown here is an example from GPL, where you see the signal is it's sweeping through the 250 kilometer wide swaths. And in fact, you see like two of the beams are being recorded by the antenna at the same time. I have to mention one thing here, that is the antenna cannot be used to transmit and receive radar signals at the same time. So whenever it transmits a signal, you will lose some radar echoes, returned radar echoes. But since the footprint kind of overlaps with each other on the ground, so when you are doing focusing, one could essentially interpolate through those gaps. And the engineering design of NISAR sort of makes this kind of gap happen here and there. So the data quality is largely unaffected spatially. So that's pretty much everything. I'll stop here and take questions.